WebGPU is a new GPU API. It can be used to render 3D scenes in web browsers. However, you can also use it for GPU computing. That is, you provide data and upload it to the GPU device, define and execute computation instructions, and retrieve the result. In comparison to CPUs, GPUs are designed to execute a lot of computing instructions in parallel. In this video, we learn how to build a simple compute path with WebGPU. We create buffers for input and output data. Also, we specify a shader with the shader language WGSL, which executes a simple computing instruction. We can define how many shaders we want to execute in parallel, and every shader gets an X, Y, and Z coordinate position. And there is also the concept of binding groups and layouts, which are some sort of mapping between shaders and buffers. If you want to get started with WebGPU in browsers, make sure you use a browser which supports that. Currently, WebGPU is still in development and is not enabled per default. I downloaded Chrome Canary and used a hidden flag to enable WebGPU. My idea for a simple GPU computing use case is inverting the color of every pixel of a JPEG image. Here I want to upload any JPEG image as a byte array, which contains the red, green, blue values of all pixels, and invert them with a simple shader program. The result should be retrieved from the GPU and then displayed on the web page. Every pixel of the image will be calculated in parallel by one of many computing units on the GPU. At first, I start with a basic TypeScript web project setup. Here I have an index.html file and an index TypeScript file. I need to install some packages with npms. So here I am installing the WebGPU types package so I can use the WebGPU API. And also I'm installing two other packages. The JPEG.js library decodes JPEGs into an array with red, green, blue, and alpha values for all pixels, and also encodes such an array into a JPEG image. And the buffer package is a dependency for the JPEG.js library. In the index.html file, I would like to add some HTML elements. The first one is the input. I define an input tag, and it is of type file, and it accepts only JPEG images. And I provide an ID for the input. And then I define two image elements, one to display the input image and one to display the output image. And now I am in the index TypeScript file. Here I am importing the methods and interfaces for the JPEG.js library, and also I am applying a workaround. The JPEG.js library is usually run only in Node.js environments, and with that I can make it run in browsers. Now I want to create a handler function for the file input. Here I said document get element by ID, and the ID is file input. And then I set on change image selected. And then I define the image selected function. So here I want to get the selected file. And I do some error handling. If not files, or files length is less than 1, then return. Also, I would like to make sure that the selected file is actually a JPEG image. Then I say if image JPEG, then I return, and I print out console log file is not a JPEG. Now I would like to display the image. Here I create a file reader. I would like to read the file as a data URL, and then I say data URL reader, and I'm listening on the event load, and I provide a function where I say document get element by ID, input image, and I would like to have it as an HTML image element. And then I set the source is equals data URL reader result as string, and then I say data URL reader read as data URL, and I provide the selected file. So let's try that out. And here I can select an image and display it. I am actually creating a second file reader. This time I want to read the file as an array buffer. With that I can decode the pixel colors with JPEG.js. So let's create the second file reader. It's a new file reader, array reader, read as array buffer. I also need to provide an event listener for that. And it's also the load event. And it's another function. And right here I can use the decode method of JPEG.js. I can say decode, and I provide the result of the array reader, result as array buffer, and I assign that to a variable. The result of the decode method creates a data which is a buffer with all red, green and blue and alpha values for all pixels. You also have the information about the width of the image and the height. Let us define another function to process the raw pixel data with WebGPU. Let's say we have a function, we call it process image, and the input is an array of type unsigned integer 8 array. So this array contains for all pixels red, green, blue and alpha values, and also we get the width and also the height of the image. And the result will be a promise of type also unsigned int 8 array. The computing on the GPU device will be done asynchronously, therefore we return a promise here. Let's get rid of the compile error. We return a new promise, resolve, and currently it does nothing. This is the to-do, and here we do the WebGPU computing. So having that process image function, we go back to the array reader with the decoded JPEG raw data, and here we call the process image function. And we create a new byte array, unsigned int 8 array with the data. We also provide the width and also the height. And then after it has been finished, we would like to process the result. So I have skipped forward, and on processing the result, we must go the other way. We must encode the byte array to actual JPEG data with JPEG.js. And then we must transform it to a data URL and then assign the data URL to an HTML image element with the ID output image. So let's verify that it works by going to this process image function and without processing the array, just resolving it and returning the input byte array. That means we do not process the image, we just return the original values. And let's see how that works. And now you see the input image and the output image. And finally we can start using the WebGPU API. At first we must get the GPU device. For that let's do this. We make the process image function async, and here we can say navigator GPU request adapter. The adapter displays some basic features of the GPU, some things like limits, and you can see how many storage buffers and texture errors you can make. And having the adapter, you can request a device. And having that device, you can start creating your computing pipeline. At first, we must define buffers. Buffers are shared between CPU and GPU, so you can add data to the buffer and then provide it to the GPU, and also the other way around. For my example, we actually need to define 4 buffers. The first one will contain the width and the height of the image. This information will be needed for the shader program, so a computing instance knows which pixel it must process. The second buffer will be the raw pixel RGBA data. The third one will be used to store the computed pixels by the shader program. And the fourth buffer is used to copy the result and to read the result by the CPU. So here we start getting really low level. Let's just create a buffer. The first one will contain the width and the height. I want to have the width and the height in a single array. So I create for that a new int32 array, and it contains the width and the height. Size array, and here I define another variable, and this is the actual buffer, GPU width height buffer, and I say device, and here I can just say create a buffer. And I actually need to provide some options. The first one I say is mapped at creation, and I want to set it to true. A mapped buffer means my JavaScript program has access to that buffer. If the buffer is unmapped, it is only available for the GPU. That way, race conditions between CPU and GPU are avoided. Also, I must specify the size of the buffer. And the size of the buffer is the size of this array in byte length. Note that the size of the buffer must be a multiple of 4, since we have two 32-bit integers, that is not a problem. And also we must set the usage of the buffer, GPU buffer usage, and we only use it as a storage buffer. Now we have a buffer and we must insert this data into this buffer. I can say on this buffer get mapped range, and setting the data into that buffer can be done by creating a new 32 integer array, providing the mapped range, and then setting this data. And then I can say this buffer unmap, and that means I am handing this buffer over to the GPU and I cannot access it anymore from my JavaScript program. And now we need to do the same thing for the raw pixel data. That means once again I call the device, create buffer, and I also say it is mapped at creation. I also set the size, and the size is this time the array byte length. Also we have to make sure that the size is a multiple of 4, because we have an array which contains red, green, blue and alpha values for every pixel. That means 4 bytes for every pixel. This is okay. And also the usage for this buffer is also GPU buffer usage storage. I must assign this to a variable, GPU input buffer. And we must also set the data with the same method as before. This time I create an unsigned 8-bit array. GPU input buffer get mapped range, and then set the array, the input area as the data. And here, of course, I also say unmap. And now let's create the third buffer. Here, the shader program will store the calculated pixel values. Const GPU result buffer, and I say device create buffer. And this time I don't need to tell whether it's mapped at creation or not. The default value is false. Size is this array, byte length, The result size will be the same as the input size. And I can say usage, GPU buffer usage. I use it for storage, and also I use it as a copy source. Once the computation has been finished, this buffer will contain the result, and I will use it to copy from this buffer into another buffer. I am doing this extra copy step in order to get along with WebGPU restrictions. So let's go ahead and create the read buffer. And it's also almost the same. I say device create buffer. It is also unmapped per default, and I said the size is array byte length. And the usage is this time different. I say the usage is GPU buffer usage copy destination, and also map read, because I want to read from that buffer. So this is the storage buffer to store the result. It is the copy source, and this is the copy destination, and it is used to read the result. Now we need to take care of the binding group layout and the binding group. So the layout defines the input and output interface for the shader, and the binding group represents the actual input and output for the shader. So let's start with the layout first. For that we create another variable, bind group layout, and it is device create binding group layout. And here we also provide some options. We must specify the entries, which is an array. And here we provide all first three buffers as input or output for the shader. So let's insert the first entry. The first entry is the first buffer, which is the width and height buffer. We define this object here, and we said it is a GPU bind group layout entry. We must define an index for it. The index is 0. And also we must specify the visibility. And the visibility is GPU shader stage compute. That means this buffer is visible for the shader during the compute stage. And also we must specify the buffer type. And it is this one here, type. And it is a read only storage, because our shader wants to read only from that. So I have inserted the second entry, which represents our pixel data. It has the binding index of 1, the same visibility, and also the same buffer type. And let me add the third entry. And it has the binding index 2, and the visibility is also the same. Now I need to set the buffer type, and the buffer type is now different. It is used as a storage buffer. So now we have defined the input buffers for the shader and the storage buffer where it stores the result, and that's it for the binding group layout. And now we must take care of the binding group, where we say which buffer is at which index. For that we create another variable, const bind group. And of course I say device create bind group. And here I must provide the reference to the layout. This is the bind group layout. Here I have also an entries array. The first entry has the binding index of 0. And the resource is the buffer, and it is the GPU width and height buffer. So with the index of 0, I can access the width and height buffer. Also, I need to specify the other two buffers. And here say binding index is 1, resource, and it is a buffer. And this time it is the GPU input buffer, which contains the pixel data. And the third buffer, it has the binding index of 2. The resource is Also a buffer, and this is the GPU result buffer. So we have taken care of input and output for the shader program, and let's create the shader program. For that, at first we create a so-called shader module, and also with the help of device we create a shader module, and for that we must provide the code. So this is the actual shader programming language code. Here you define the shader instructions. For the time being I skip this. So once I have created the shader module, I need to create the computing pipeline. And for that I say constant. I want to have another variable compute pipeline. And also I say device create compute pipeline. In here I must provide a layout. And I can create the layout also with the device create pipeline layout. And in here I must set the bind group layout. That's the one what we created before, bind group layout. And also right after here I must provide a compute attribute. And here I must set the shader module. And I must provide the entry point. And the entry point will be the main function. So what that means is we have a shader module which contains shader computation instructions. It is expected that it contains a main method which acts as the entry point for the shader computation. And we provide the bind group layout which defines the input and output buffers. So this shader has access to those buffers. And now let's talk about the shader programming language WGSL. WebGPU uses the shader language WGSL. There exists an official documentation, as you can see here. The language may remind you of C or Rust and is some sort of low-level-ish. There are some examples which you can find on the web. So let's see what I have made. So at first there is a main function expected, which is the main entry point of the shader program. So let's go ahead and create one. We say fn main, and this way we have the main function. Also we must specify the stage of the main function. So over here we must provide in double square brackets, we must say stage, and it will be executed during the compute stage, since we have a compute pipeline. Also there are some built-in input variables. We can say the main function will receive an input variable, and here in square brackets, double square brackets, we must say we have a built-in. So with the built-in call, we can inject a built-in input variable. We must provide the identifier of the built-in input. So with this global invocation ID, I want to have the global identifier of the computing instance. I must also specify the variable name under which I want to access this input. I say it is global underscore ID, and it is of type a 3-dimensional vector which contains unsigned 32-bit values. As I have already mentioned in the intro, you can span a 3-dimensional space of shader computing instances. Every instance will have an X, Y, and Z position within that space. With the global invocation ID, the instance knows its X, Y, and Z position. You can create a single computing instance with X, Y, and Z being only 1, that's the default value, or you can create one-dimensional space where X is greater than 1, or a two-dimensional space where only X and Y are greater than 1, or a full 3-dimensional space. For my use case, I can work with either a one-dimensional space or a two-dimensional space. I choose to work with a two-dimensional space, so my shader program has an X and Y position, and I will use the pixel array as a matrix. So within the shader program, you can also define structs. For that, you must say in double square brackets, you define a block, and then the keyword struct, and then you can provide a name for the struct. I choose the name size. And within the struct, you define the members, and it will have one member, which is named size, and it will be of type two-dimensional vector, containing 32-bit unsigned integers. So with that 2D vector, I have an x and y value, and this will be the width and the height of the image. Also, let me define a second struct, and I name it image, and it also has only one member, and I call it RGBA, and this is an array of the pixel values, and it is an array with unsigned 32, and here I must also set unsigned 32. So this array will contain 32-bit integers, and 32 are 4 bytes, and the 4 bytes are for red, green, blue, and alpha values for every pixel. And now we can start mapping the buffers to these structs. So down here in double square brackets, I want to access the binding group with index 0, and I want to have the binding also with index 0. That will be the first buffer containing the width and the height of the image. And also here I must say var storage. We are accessing a storage buffer, and also provide a variable name. This is width, height. And here in double square brackets, we must set the access type, and we are reading from that buffer, and we are mapping it to the size struct. And now we must map the input pixel array to this struct, and also the output buffer to this struct. For that we say also in double square brackets, I am accessing still the first group, and now with the binding with the index 1. This is the pixel array. We are also accessing a storage buffer. The name of the variable is input pixels. The access type is also read, and the struct will be the image struct. So now I need to do the same for the output buffer. I can actually copy paste this line here. I want to have the binding with the index 2. This is the result buffer. I rename the variable to output pixels. The access type will be write. So now I have defined the input and the output for the shader program. I want to read a pixel from this buffer and then calculate the new values and store the pixel into this buffer. So given the x and y coordinate of the shader program in this variable, and given the width and the height of the image, I can calculate the index at which I want to access the input pixel. So in the main function here, I create a new variable and I call it index, and it will be of type unsigned 32. So in here I must transform the two-dimensional position of the shader program into a one-dimensional position to access the array with the pixels. And here I can say global ID, and I can access the X position of my shader program plus global ID Y position times. Now I need to know the width of the image. I access the width and height variable, and I say size. The size is this member here, and I want to access the X value. So I'm going from an X and Y position of the shader program to an array index position. Now having that index, I can access this input pixels variable, and then I can say RGBA and use the square brackets to use this index. And I want to invert all values at this position. And to invert it, I just use the maximum value of a 32-bit integer and then subtract the current value. Also don't forget to set the semicolons here. So with this, we have the inverted pixel value, and we must assign it to the output buffer. We can just access this variable here, access the RGBA array using the same index, and assigning the result to this pixel value. So that is the final shader program, and I think we are done with the hardest part. So now we are almost done with the compute instructions, just a little bit more to go. So let's just go over here and proceed with the rest. And here we must create a command encoder. Let's create another variable, command encoder. And once again we use the device to create a command encoder. without any parameters. Now another variable. Now this time it is the path encoder. And we use the command encoder to begin a compute path. And having that path encoder, you can set the pipeline. It's this compute pipeline. Also call path encoder set binding group. This is the binding group which we have created before. And also you must provide the index for that binding group. It is the index 0. Like here, we are accessing the bind group with index 0 in the shader program. Also say path encoder and then call the dispatch method. And here in the dispatch method, you define the x, y, and z. With those values, you define what kind of dimension you have. You must provide at least an x value. The y and z values are per default 1. The x value will be the width of our image. And also I want to provide the height of the image as the y value. With that we have a two-dimensional space where x is the width of the image and y is the height of the image. And also we must say path encoder and end the path here. So finally we have defined the computing instructions, the buffers, and also specified how many computing instances we want to have and what kind of space we want to span. After the computation has been done, we want to copy the result into another buffer. For that, we also access the command encoder and we say copy buffer to buffer. And of course, we must provide some parameters. The first parameter is the source buffer. This is the GPU result buffer. The offset is 0, and then the destination buffer is the GPU read buffer. This is the fourth buffer which we have created. The destination index is also 0, and also the total length is the array byte length. And finally we can access the device again, access the queue of the device, and then submit a command buffer. And it is an array of command buffers. And we can create a command buffer with command encoder finish. So at last we must read the result from the read buffer. For that we can just say get the GPU read buffer and call the map async function. And here we must provide the map mode, GPU map mode read. And since it is an async function, we must provide a handler and says then this function here. So the data will be read when the computation has been finished. And then I can say resolve the promise of the overall function. And we would like to create a new unsigned int 8 array. And it will contain this GPU read buffer get mapped range. So finally we have created a more or less simple WebGPU computing example. Let's verify that it actually works. So let's take a look at the web page. Let's select an image, for example this butterfly, and that's looking really good. Also another image. So this is the inverted version. Alright, that's it with the WebGPU computing example. It's pretty low level, but that's just how it is.